All right, so what is gained and what is lost with 63-bit integers? September 29th, 2014. This is a long time ago. Almost every programming language uses 64-bit integers on a typical modern Intel machines. OCaml uses a special 63-bit representation. How does it affect OCaml? Oh my goodness.
Before we go, I want to hear your guess.
My guess is that it speeds it up because my guess, just hear me out on this one, because they have a garbage collector, 1 bit is reserved for the type. My guess is they're implementing some sort of SME, some sort of small integer, something that allows them to do something clever so they don't have to follow a pointer for every single thing. That's my guess.
Yes, you're on the right track, at least, for sure. So I think you'll be pleasantly surprised with the trade-off.
Okay, and plus 63 bits is probably enough. The thing, what I mean by that,
it's really true though.
It's really true in most people's integer experience, because if you're doing financial stuff, you're using strings, right? You have to be absolutely precise, and you have these really long string calculations and these libraries devoted just to like perfect precision financial stuff. And if you're doing integer representation, you're not going to just be tossing on a quintillion on the screen. No one's can read that.
You guys could fit your users in an 8-bit integer max. Like, you'll be fine.
Yeah. Your users don't even, let's just face it, a 4-bit is probably good enough for most people's users.
It can be a bool. Am I logged on? Am I logged off? It's mostly my user table.
Is it me or my test users? Yes or no? All right. OCaml int memory representation. Most of OCaml's types are in memory representation as a header followed by data. The header is a 64-bit integer containing the length of the data and a tag. A tag is a rough classification of the type. The only OCaml's type which differs from this are ints and sometimes floats. Okay, so I might be on the right track. I'm using my knowledge of what V8 does, and that's why I'm guessing this, because they have SMEs as well. Floats normally have header and data being the value of the float itself. This representation is called boxed. Oh, man, look at that period outside the double quote. Did you know that is apparently a UK versus America thing?
I heard that. I think objectively, dot outside is better. Because, like, you're quoting the boxed, right? And then you want to put a period at the end. Personal opinion.
You just said objectively and now personal. Which one is it, TJ?
Well, it's Twitter, so we can say both.
My opinions are objectively better.
Well, it's the internet, so like whatever I think is right and whatever someone disagrees with is wrong, and not only wrong, morally repugnant.
There we go. My opinions about software engineering are objectively better. And tweet.
Dang it. You're welcome. That's going to be $3 in your pocket from this tweet.
So many impressions. All right. If a records field is a float, records data will actually contain a pointer to the float data, right? So this is one of the reasons. So when you're doing actual like math and stuff to make it fast, to have to follow every single value somewhere would just totally suck. Especially if it's a value that doesn't need to be even on the heap at all. It just is crazy, right?
Right.
The only exceptions are records with only floats and floats arrays, whose data instead of pointer contains the value of floats. This representation is called unboxed. In other words, do you have a box that contains the offset to the value, or is the thing itself the value? Values of type int are never stored as header and data, boxed. Int x is stored as 1 or x shifted by 1 with an or 1. Okay, first bit. So it's a first bit check. Where double over or double left or what a left shift is this in bitwise, blah, blah, blah. Okay, hence its least significant bit is always set. Pointers are
Chat
word
doesn't
aligned.
know what this means, though.
Chat doesn't know what this means?
You should probably draw it in GIMP for him.
I can draw it in GIMP for them right now. Okay, look at that meme, though. Can we all just appreciate that one? That was my HTMX meme, which I thought was one of the best memes.
Except it was me.
Yeah, that was you.
I'm donating so many impressions to you. It's incredible.
The reason why I have followers is because of you. All right. So if you can imagine, here's a value. Let's just say our value is 1. This is a value 1. Yep. In our world, in our normal decimal counting system, if I had 1 and I multiplied it by 10, it's just 10. If I multiplied it by 10 again, it's 100. In binary counting system, since base is 2 instead of 10, multiplying by 2 is the same thing as effectively left shifting. So when I multiply 1 by 2, I get the answer of 0, 0, 1, 0. If I multiply by 2 again, I get 0, 1, 0, 0. In other words, it's the same thing as multiplying by 10 in our counting language, which a left shift If I left shift by 1, it's the same thing as multiplying by 2. So when you pass in x, you left shift by 1, you move all the binary over, right? And then you OR 1. OR effectively is a truth table of, let's just call it A, B, 0, 0, 0, 1, 1, 0, 1, 1. The values are 0, 1, 1, 1. In other words, if any of them are a 1, it becomes a 1. So by ORing a 1 into this, this means if your value, let's just say x was 0, 1, 0, 1, we left shifted it over, that'd make it 1, 0, 1, 0, and then we ORed 1, that'd make the final value 1, 0, 1, 1. Boom.
Correct.
Simple as that. So if you've never done some bit stuff, it's really good to do it. It's really great for protocols and stuff like that.
And CPUs are really fast at this, by the way.
Yeah.
Like, they're really fast at this, and in general, it can always be pipelined. So that's just something to think about when you're thinking, that seems like a lot of extra stuff. Actually, CPUs are pretty good at this.
These effectively become single instructions, right?
Yeah.
They're just like defined basic instructions, so they're very, very fast. Whereas when you have to go follow a heap pointer and do stuff, you're doing a lot more. Typically, when you're doing, if everything's on the heap, it takes a lot more effort.
And so where you got to compare this as well, we're going to get to it, I'm sure, but like you got to compare it to memory access, right? So that's basically the difference, right? They're going to try and trade something for how often they have to go do memory access, right?
Yeah. Pointers are word aligned, so they'll never have this bit set. Hence, how ints and pointers are discerned. It is assumed that, by the way, word aligned for those that don't know, let's just say you had a big block of memory and you're on a 64-bit system. You can imagine that you do something that is not, or really any bit system. So some people can take this at the 8-bit boundary. Some people, you can do it at depending on where you're at. So 64-bit boundary would be an easy one to do. You would never store, like, say your item only takes up 8 bits. You would never store it at the second byte, your next item. You'd go all the way over to the next spot, which would be 64 bits. That's what Rust does with structs. It turns out it can be a lot faster for CPUs and stuff like that, and blah, 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 blah. I don't really understand that.
And just conceptually, you'd think it wouldn't be because you're taking up more memory or something, but actually it's just like the CPUs are really good at doing those things.
Yeah.
Right? Is they're optimized for that case.
Yep. Pointers are word aligned, so they'll never have this bit set, hence how ints and pointers are discerned. It assumes that much of the typical data is integers, so this is done to significantly improve performance. There is no need to dereference a pointer when getting an int. No memory allocation is needed when creating ints. Less work for the garbage collector. Less memory fragmentation. No memory is needed for int headers. I assume that's because all ints are just copied everywhere. You don't actually need to have any form of collection. They're just copied and immediately got rid of anytime something leaves, right? Distinguishing whether a value is int or pointer is simply doing this test right here. So this feature doesn't slow down garbage collector, polymorphism hash, polymorphic compare, and whatever else structurally inspects data. One should note that this doesn't apply to types int32 and int64, which are always boxed. Oh, I didn't know that. Is there that's because there's an int type, right?
Yeah, there's just an integer type that you would normally use unless you have some really particular reason about saying that it actually has to be 32 bits or actually has to be 64, right? And well, we won't talk about it today. Maybe later we should read the Jane Street article, or I don't remember if we actually read the one for unboxed types. But there's work to be able to say certain things will also be allowed to be unboxed, which is really cool. But that's for a different day.
Yeah. I assume this is along the lines of the life cycle stuff.
Yes, it's sort of in that same vein of when you want to be able to do something in particular and some certain constraints, you can actually get a lot of performance improvement by doing these things, right? By not allocating them on the heap. Yep.
Let's see. Having the extra bit comes with a price. Arithmetic operations are more complicated. For example, x plus y is translated into the CPU instructions x plus y minus 1. X times y is translated into the CPU instructions x shifted over by 1 multiplied by y minus 1 plus 1. I don't understand that quite yet. I'd have to look at that on paper to kind of...
They're basically just you can just start with x. It's actually, x minus 1 times y minus 1 and then do the arithmetic with each other, and then you can actually figure out what they go to, but then they just get stored correctly, I think. But keep in mind as well, this is actually at compile time, not at...
Yeah.
Or you have to run this check, right? But it's not figuring this out on the fly.
Yeah. All right. This thing is translated to the CPU instructions this. That's a lot of work. There's a lot of arrows shifting all over the place.
Yep.
X, was this left shift left? What is LSL?
I think so, yeah. That must be left shift left. Yeah.
That doesn't make any sense. Left shift left. What is LSL?
No, I don't know.
What is LSL?
I don't know. Logically shift left. According to low level learning. I trust him. He's got low level in the name. He's a genius.
What's the difference
Pretty cool
between
YouTuber.
what is a logical shift left? Does that just simply mean like a zero fill? I don't know.
I'll wait for low level learning to type something in chat. I'll copy exactly what he says out loud, and then I'll sound really smart. I'm waiting. Logically versus arithmetic. Yeah.
Nailed it. Because I know bitwise. Let's see. Arithmetic rotates. Oh, really? Why would arithmetic rotate? Okay, I'm not going to answer that question.
That's fine.
I assume when he says rotate, it means that if you had a 1 at the end,
it
goes all the way around.
Right.
Wild. Okay, so you see all these things. Obviously, doing stuff creates more instructions to do. You can't simply just X plus Y because they're stored a little bit goofy. You'd have some weird rollover that happens.
Yep.
I think I understand the -1. Actually, I do understand the -1. Check this out.
Show him.
Check it out. Let's just say that we have 0 plus 0. That means it's going to look like this. So 0 plus 0 is going to be 0, 0, 0, 1 because it's an integer. 0, 0, 0, 1 because it's an integer, which means that its value would be 0, 0, 1, 0. Now -1 from that makes it 0, 0, 0, 1. It goes right back to it. I get that because these two added become 2. And so to get it back over, you need the -1. Okay, I see that. So it's just a bunch of arithmetic fanciness over trying to preserve the value of whatever to preserve that 1 in the first position. Okay.
Right. And like that happens, the instructions get generated when you compile. It can like figure out that you're adding 3 numbers together or 2 numbers together or 5, and it like does the simplified version for those things, right? So like the compiler will do that as you go. It's not like it's encountering an unexpected plus because it's an interpreted language, right? So that's like one of the things you have to consider is it's not always as bad as you'd expect. And once again, CPUs are really good at pipelining.
Yep. All right. Sometimes this penalty is small or non-existent. For instance, there is no need to fix the bit X plus Y minus Z. Only fix 1 bit is needed for all 5 additions. Yep, that makes sense because this is an even amount of additions. Therefore, you have to -1.
Yep.
Potentially, I'd have to think more about that. Maybe you might.
It's okay. They're just basically saying it doesn't seem as bad as you might think for like lots of the common things where you're just like adding 1 number, multiplying a few numbers, etc. It seems good.
Yeah. All right. Another help is the Intel CPU instruction li. Which can compute the sum of 3 integers with a single instruction like X plus Y minus. Oh, really? I didn't know that. Unfortunately, Lee became very slow in the recent generations of CPUs. Intel doesn't suggest this will change. This benchmark TestML tries to estimate the difference in performance. The results from Sandy Bridge show about 2x speed difference in arithmetic operations. Assembly can be examined compiling using OCaml opt-s ML. Oh, cool. That's cool that you can go check out all those things.
Yeah, that's 2014, so like it may be quite a bit different now, but yeah.
A decade of CPU probably is a bit different. Just a little bit. Agner's instruction table shows the difference is even bigger with later generations of CPUs. For instance, Haswell can do 4 integer adds per cycle versus 1 Li. Conclusion. The benefits of unboxed ints are amazing. On the other hand, arithmetic operations are significantly slower. How much do arithmetic operations affect the average program? Could we have a solution that would keep int unboxed to have the fastest arithmetic operation? Question mark. Well, I mean, one thing that they're not talking about in here is if they didn't do it this way, you still would have to go fetch. You'd have to follow a pointer to the value.
Yes, I mean, that's like they only mentioned it casually, but that's like the point. So we should probably like clarify, like maybe draw like a block of memory, right? And like think about what it looks like if you actually only have basically pointers to some other spot, right? You're basically wasting so much space because you're just going to have a pointer that's word aligned. So like 64 bits usually that points to some spot in memory to an integer that could be 64, right? So it's like, Yeah, and
the one thing I don't understand, so I'm not like a huge assembly guy. I've done assembly once in the past. I've only ever gone as low as C. Typically, I've never gone much lower than that. And so in this world, like when you're doing something like this, like X, if this was the way, right? So let's just pretend this is X, this is Y. And then, of course, this is 1, which 1 is like a constant. We'll just call it a constant, right? And if you're doing something like this, if I'm not mistaken, in the assembly world, what's going to happen here is that you have to effectively like load X onto a register. You have to load Y onto another register, right? I don't know, whatever that's called. And then you do some sort of like add operation. And then you have to do some sort of, maybe there's some sort of -1 operation that can just be done, and boom, you got yourself an answer that's on some other register. That's like my basic understanding, is that you have to push things onto values and do operations on those values. I'm not sure how correct I am on that, but that's my kind of little box I've drawn around it in my head.
Yeah. Right. And so the difference is, right, there's two main things that are sort of like different than when you do this trick. Is one, the garbage collector always knows that it doesn't have to go follow stuff to different memory to clean it up. So that's like a huge win, right? Like you're done with this integer and you want to get rid of it. It sees that it's an integer, right? And it can just be done basically, right? So there's like all this extra stuff that you don't need to do because you know that for sure it's an integer without having to go follow some pointer, right?
Yep.
And then the other thing is like, if you load, a bunch of integers in a row, right? Because you're going to go do a bunch of stuff, that's all going to probably land in the same like cache hit for your CPU, right? So then like, all your integers are like next to each other because you did something with them together or whatever, right? And then you do something. You don't have to go find wherever that's the memory fragmentation part, right? Of like having to go track those down.
Yep. Whereas if we were to do this with everything still being just a heap object, even your 1 theoretically would be a heap object, where you couldn't just load
it
X.
would have to be.
You'd have to
There's literally no way to represent it without having some way either to say in this one word, right, it is either an integer or not, right? So that's the nice thing.
Yeah. Everyone in chat's trying to correct us on like, actually, this is how these things work. I have no idea about how these things work, okay, just to be completely real. I don't know how these things work. Look at this. He's using all those fancy things, EAX. I don't know what these extended A registers are. Okay, I don't know what they do. I don't get this, right? But I would assume that this load X becomes significantly more complicated when X actually is a pointer over here to something.
It wouldn't be called load X anymore. You would have to like go find what the pointer is.
Yes.
So it would just not be like
some sort of load deref
I think
business that has to go on there. And then on top of all that, this also would have to have some sort of wrapper value on top of it that the garbage collection would then know how to point to it. So minimum, your one value right here would have to be 3, CPU something sizes, right? They'd have to be probably even more than that, probably 4 64 bits to represent your small little number, to just represent number 1, because first you need your pointer address. Then this one's the actual value stored in 64 bits. Then you have some sort of tag right here. Then you'd have some sort of thing that that is stored in the GC that points over to this. So there's like a lot of steps that have to happen. So this is
and
why
then
it's
you
so much
just
more
make
efficient.
integer stuff really slow, which is like usually not what you want to do. So there's
typically you don't want to do that.
Yeah. So that's the other thing too, actually, that this makes really cool is that OCaml's memory model is actually really, really straightforward, right? Because you're basically saying, look, you either there's a few things that can be unboxed. They're shown by being this, right? So it's like, okay, so now you know the only things that can actually just be like in this word, or it's something that's heap allocated and you go find it and look it up, right? And so like, oh, that's actually a really like straightforward and simple memory model that's easy to understand and work with. And so that actually leads to very, very cool stuff, I think, as opposed to like, it's well specified what the memory model is, which is cool. Yeah. Low level. Were we doing okay? Did we do okay?
How do we do?
Maybe we should get him in to come tell us if we did okay.
You got it right.
We got it right?
Okay.
Never mind.
Go.
Get
let's
out
go.
of here.
We don't need you. We never needed you.
Never mind.
Get him out of here.
You should have told us
Karen?
we were wrong.
Hey, you're a mod. Can you ban yourself? Can I get a quick ban on yourself? By the way, if you haven't,
should have told us we were wrong. Classic.
Classic ban. TJ would have got that so easy. If you've never done it, go to Low Level Learning. Check them out as well. TJ, you're also on here,
true.
Right? You're also
at Tej_DV. You can find me there.
Yeah. Okay. Awesome. Fantastic. So TJ, you stream too, right?
I do on Twitch, believe it or not.
What? Awesome.
And this week I'm going to go talk at Jane Street about NeoVim.
We just got done reading an article on Jane Street.
Incredible. I know.
What are
Not
the
sponsored, but
chances?
should be.
Should have
Hashtag
been.
not an ad, but should be.
I know. Hashtag Jane Street. Can you just pay me for this? What do
Yeah,
you
for
think?
real.
Come on.
I'll bring it up when I'm there.
Yeah,
when I'm there this week, by the way.
Talking about what? Let me guess. Neovim?
Neovim, I'm on Core, by the way.
Damn. All right. The
Maybe
name.
you guys have heard of Telescope? The Telescope agent. See ya.
The name is TJ wrote the telescope agent. All right.
Tom Diesel. See ya.
See ya. All right. Take care, Teach.